session. Today I am going to teach a theorem from the first chapter, Real Numbers. The theorem is the fundamental theorem of arithmetic. Before starting the theorem, you should know what are prime numbers and what are composite numbers. Already you have learned in earlier classes, junior classes, about prime numbers and composite numbers. Anyway, I shall discuss once more. So, consider the number 13. 13 equal to, we can write it as 1 into 13. So 1 and 13 are factors of 13. It has only 2 factors. Okay? And such a number is called a prime number. A number having exactly 2 factors. So it is a prime number. Now another number says 17. 17 we can write it as 1 into 17. It has only 2 factors. 1 and that number. It has only 2 factors. Okay. So 17 is also a prime number. So a number having exactly 2 factors. 1 and the number itself. That is a prime number. Okay. Then considering a composite number. Now 6. 6 we can write it as 1 into 6 or 2 into 3. 2 ways we can write it as a product. So here 1, 2, 3 and 6. 1, 2, 3 and 6 are factors of 6. So it is a composite number. It has more than 2 factors. A number having more than 2 factors. That is a composite number. So a number having 2 factors. It's a prime number. Number having more than 2 factors. It's a composite number. I think you remember, all of you remember this thing. Now we can come to the theorem, that is the fundamental theorem of arithmetic. See the statement of the theorem. Every composite number, okay, every composite number can be expressed as the product of primes. Every composite number can be expressed as the product of primes, and the factorization, that factorization is unique. Apart from the order in which the prime factors occur. Okay. Now, first we can take an example and I shall show the statement by taking an example. Okay. So, consider the number 300. Consider the number 300. Let us see its factorization. 300. We can divide it by 2. 2 is the least prime, smallest prime. First try to divide it, say an even number, so we can divide it by 2. So dividing by 2, we are getting 150. Again, it's an even number, we can divide it by 2. 75 divided by 3. 25. Again, next step, divisible by 5. So 5 into 5. Okay. So, we can write this 300 as 300 equal to 2 into 2 into 3 into 5 into 5. Okay. So, this is the factorization of 300. Now, see all these factors. All the factors are prime numbers. All the factors are prime numbers. 2 is a prime, 3 is a prime and 5 is also a prime number. So we can factorize this composite number 300. Okay. This is a composite number 300. And we can factorize as the product of prime numbers. We can factorize it as the product of prime numbers. Because 2 is a prime, 3 is a prime, 5 is a prime. That is the first part of the theorem. Every composite number can be expressed as the product of primes. We can write every composite number as the product of primes. That is the first part of the theorem. You can take any example, any composite number and find out the prime factorization. You can see that. We can write it as a product of prime numbers. Take any other example other than this 300. Would take any other number and try to prove that it can be expressed as the product of primes. That's possible. Okay. Now coming to the second part. Again, 2 into 2 we can write it as, if you want we can write it as 2 square, 3 raised to 1, 5 into 5, 5 square. All of you know. So here how many 2's are there? 2 2's are there in the factorization. 1 3 is there and 2 5's are there. If everybody do the factorization, you will get the same factors. 2 2's will be there, 1 3 will be there and 2 5's will be there. Okay. So that is the factorization. We can write it in one and only one way. There is one and only one way of writing the factorization. One and we cannot say 7 is a factor of this number. No, 7 is not a factor of the number. Only 2, 3 and 5 are factors of the number. So there is one and only one way of writing the product, and so we can say this is unique. One and only one way or unique way of representation. So there is a unique way of representation like this. So and the factorization, that is the second part. The factorization is unique. There is one and only one way. We cannot write it in any other way. So that is unique. The factorization is unique. Okay. And the last part, the order in which the prime factors. Okay. No problem in writing this as 5 square into 3 into 2 square. We can change the order of the factors. 5 square, write it first, then 3, we can write second, and 2 square. Okay, that doesn't matter. We can write it in any order. So this is given as the theorem. We generalize and write it as a theorem. This fundamental theorem. That is, here we have seen the composite number 300 can be expressed as the product of primes, and there is a unique representation. There is one and only one way of representing the number, and we can, if we want, we can change the order of the prime factors. No problem in changing the order of the prime factors. So that is given as the theorem. That is, every composite number can be expressed as the product of primes. Here we have shown for 300, and the factorization is unique. There is one and only one way of representation. That is unique, and the order, no, that doesn't matter. We can write it in any order. So this is fundamental theorem of arithmetic. Once more I shall repeat the statement. Every composite number can be written as the product of primes, and the factorization is unique irrespective of the order in which the prime factors occur. Okay, I think you have enjoyed and understood the theorem. Okay, learn the theorem once more. Learn the statement of the theorem. Okay, thank you children. Thank you all.